Hello, in this video I'm going to go over a particular aspect of chi-squared test for contingency tables, which covers the cases where the expected frequencies fall below 5, because the chi-squared distribution really doesn't approximate the test statistic x squared particularly well in the cases where the frequencies fall below 5. So the convention is that we start combining frequencies and combining categories. Now, in the following example, we're going to do the actual combination of categories is pretty obvious. Occasionally, you may be faced with a choice of where to combine things, and in this case, in other cases, it's really takes sometimes worth taking a bit of thought on which categories to combine. For example, I've written an example there about music categories. If you're talking about favorite music, you wouldn't be sensible to combine hip hop with classical, but it might be sensible to combine rock with pop or jazz with blues. And if it was things about favorite subject, or for interest in school or college, biology and chemistry combined is probably more sensible than combining, I don't know, media studies and archaeology. So there is sometimes some thought to be had in which ones to combine. Not so much in this one, because the actual categories we're going to combine are these, and both of these rows turn out to have quite small expected frequencies, and this one falls below the critical 5, which is where we start saying we really must combine categories in order for the chi-squared distribution to be justified. Okay, so we're going to do this test. I'm assuming that you've already seen, you kind of know how to work out the test statistic for chi-squared. If not, have a look at another video. This follows on from a video I've already done, which goes through the detail of how we use that formula there for working out the test statistic for a chi-squared test. Okay, so let's get on with it. Let's set up our hypothesis. First of all, the word independent is used in the wording. I prefer to use the word independent in many cases anyway, rather than association. But here, the kind of null hypothesis is that the treatment, the outcomes, after 6 months each has then assessed the outcomes, the patient outcomes are independent of the treatment. Whereas the H1 is the patient outcomes. Don't worry, it's just the patient outcomes are not independent of the treatment. Obviously, if the word associated is to be used, then we would kind of say these are not associated, and here we would say that they are associated. So it's kind of the opposite. So there's our null hypothesis. Now let's work out our expected frequencies. Let's just pull down the table from below and then just add the rows and columns to start working through this. So all we need to do is actually add all of the rows and all of the columns. So 16 plus 4, 20, 32 here. And then we do that for all rows and all columns. So it's these numbers that we use to work out our expected frequencies. And the formula that we use, which I kind of explained a little bit more detail in the last video, is that you just multiply row total times column total over grand total. And just as a useful check, actually, it is useful to check that the rows and the columns add up to 100, just to check you haven't done any of the adding incorrectly. So, for example, this number, the number in that cell for the expected frequency will be 32 times 37 divided by 100. Okay, and that comes to 11.84. So we have 11.84 for this number here, which corresponds to the number, the expected frequency for that cell. And then we just do a similar thing for all the other cells. So I'll just do that now. Okay, so there's our expected frequencies, and as I kind of gave the heads up to at the beginning, we've got this is less than or equal to 5. It's less than 5. Okay, and so we need to combine. Now, before combining, it's worth thinking about where is it justified to combine with a particular category, and certainly to combine no change with slightly improved is not too much of a problem. So what we need to do is combine basically both, produce two new tables really, one with the combination of these two, so these two cells, and also combining with our expected frequencies all of those. So I'll just write those up now as well. So here are the two tables after combining, and notice now we don't have any expected frequencies less than 5. So we're good to go with our test statistics. So which is x squared is the sum of the observed minus the expected squared over the expected. So let's just write down each one of them. So we've got 12 minus 11.84 squared divided by 11.84 plus 16 minus 11.84 squared over 11.84 and so on. And let's just write the last one down, which would be 9.62 take away 16 or 16. Let's be consistent. It wouldn't matter because we're squaring it anyway, but to be consistent, that's 16 take away 9.62 squared divided by 9.62. So we've got 9 cells to complete. Let's write down the 9 values. Okay, so you might want to check that you've got the same numbers as those and how you got the numbers, and those add up to our test statistic 10.51. Now we need to compare that with our corresponding chi-squared critical value, which we need the tables for. So I'll just bring up the tables. Let's just talk about degrees of freedom before I do that. Degrees of freedom, I discussed this a little bit in the last video, but in the context of contingency tables, we basically times by the number, take one off the number of rows and one off the number of columns and take it from there. Now here we've again got a 3 by 3. So we're going to do 3 take away 1 times by 3 take away 1, which is equal to 4. So we're looking for the corresponding value at 5% for our test. I think, remembering it was 5%. Yeah, 5% for our test. We're looking for our corresponding value from the tables for that chi-squared value, for that value of our test statistic. So let's bring up the tables. So we're looking at 4 degrees of freedom in this row and 5%, the upper 5% tail. Remember, we never really use these. They're kind of, they're there just almost convinced to make sure you know what you're doing. So we are looking at the up tail. So the critical value is 9.488. I always like to draw my chi-squared distribution. And we've got the value here, which is our critical value, which is 9.488. It's right hand out our chi-squared value with 4 degrees of freedom at 0.95 is equal to 9.488. Again, this is our critical region. We're in our critical region because our value is 10.51. Let's write that in as an inequality. 10.51 is greater than 0.488. So now we need to conclude. So again, remember, this is a critical region, which is where the set of values for where we reject H0. So we reject H0. There is sufficient evidence that, and we use the word independent in our hypothesis, so that the patient outcomes are not independent of treatment. Okay, so that was a video just talking about combining cells. There's one more we're going to do after this on contingency tables, which is where there's a kind of another glitch when we actually have a very small 2x2 table where there's other inaccuracies that can kind of come in, and there's this question of whether to use Yates correction, which we'll be covering in the next video. Okay, so that's it. Until then, bye.